I am extremely honored to receive and accept the BBVA Foundation Award in Basic Sciences. I am humbled to share it with Professor Claire Voisin, whose work I greatly admire. Our work belonged to two different branches of geometry, algebraic and symplectic. In the last few decades, thanks to the work of several great mathematicians, notably Mikhail Gromov and Maxim Kontsevich, these two areas had seen a lot of progress, each side contributing to the development of the other. While Professor Voisin's work is on the algebraic side and mine is on the symplectic one, our research contributed to the development of the subject towards each other. Symplectic geometry and its cousin contact geometry were brought to life by needs of classical mechanics and geometric optics, while later deep connection with quantum mechanics and quantum field theory were also discovered. At the end of 19th and the beginning of 20th century, Henri Poincaré was the first to realize that many qualitative problems of celestial mechanics could be reduced to problems in symplectic geometry. In particular, his so-called last geometric theorem, proven by Berghoff already after Poincaré's death, linked a problem about existence of periodic orbit in the three-body problem to a problem about fixed points of an area preserving transformation of an annulus. 100 years later, the development of symplectic geometry and topology partially realized Poincaré's dream. When mathematicians explore mathematical world, they often encounter problems of two types, which I call flexible and rigid. On the rigidity side, one deals with discovering the laws of nature in this world. In other words, constraint to which all constructions in this world have to satisfy. On the flexible side, mathematicians are searching for construction on the frontier of what is possible. One of my contributions to the development of symplectic geometry and topology was pushing the flexible and rigid side towards the ultimate frontier between them. In particular, I extended Poincaré's last geometric theorem from an annulus to all surfaces, thus proving Arnold fixed-point conjecture in that case. Along with Gromov, I established the first rigidity result in symplectic topology in dimension greater than 2. I defined the so-called tight over twisted dichotomy in contact geometry, which has driven a lot of research in this area. I am also proud of our joint work with Helmut Hofer and Alexander Giventhal, which introduced a new formalism of symplectic field theory. Symplectic field theory found application to many geometrically interesting problems on the borderline between symplectic and algebraic geometry, as well as in the theory of integrable systems. In the course of my mathematical career, I benefited a lot from my interaction with several Spanish mathematicians, including Jesus González, Francisco Presas, Álvaro del Pino, Daniel Álvarez Gavela, Roger Casals, some of whom were my PhD students or postdocs. Hence, it is especially significant for me that I am receiving this prize from a Spanish foundation. I am extremely grateful to all my mathematical teachers, beginning from Nina Mitrofanova, whose mathematical circle in Leningrad turned me to mathematics, my PhD advisor Vladimir Abramovich Rokhlin, and my friend and teacher Mikhail Gromov, interaction with whom transformed my view of mathematics. I was and I am still lucky to be able to collaborate and learn from many great mathematicians. I am also learning a lot from my Stanford students, 41 of whom already received their PhD and have their own successful careers in mathematics, science, and industry. Finally, I want to thank my wife Ada for her love and support through our life together in Leningrad, Syktyvkar, and Stanford.